Alright, good morning. I'm going to turn off people's chime when they come in, because people seem to get dropped sometimes and then come back in and we get chimes going all morning long. Alright, how's everyone doing? Doing good. Glad to hear it. So let's take a look at ODP 214. This is almost the same as 213, except that our hash function takes two arguments now. So it takes the key you want to hash, but it takes a second argument, which is the probe or attempt number. Right? So your prototype looks like a char star and an int. And the only difference in the behavior of this function is it adds the square of the probe to the final result and then reduces mod 31 again. So for example, if you call this hash function with a probe of 0, you get exactly the same value that you got with ODP 213. But if you call with a probe of 1, your values will be increased by 1. So instead of getting a 4 when you hash hello, a probe of 1, you would get a 5. If you call with a probe of 2, you would get something 4 times beyond what you started with, so a 4 would turn into an 8. If you call with a probe of 3, your original hash value gets increased by 9, which is 3 squared. So instead of a 4, you end up with 13. If you call with a 10, your original value gets increased by 10 squared, which is 100. So your hash would be 104, which you reduce mod 31. Let's see, 104 gets you down to 71. Take off another 31, that gets you down to 40. Take off another 31 3 times, 50, 31, 11. Yeah, it works out. So just reduce mod 31. So what does this look like mathematically? So take your usual sum from 0 up to your string length minus 1, so all the characters. Add up the ASCII codes. When you've done that sum, or if you want to initialize your running sum, either way, add the square of the probe and calculate all that mod 31. So it's a pretty minor tweak on ODP 213. Let's see, so maybe I'm not understanding the overall picture very well, but are there cases where you'll have open spots in your hash but you never actually fill them because your probes and hash functions are set up? That is possible, right? So, so yeah, let's talk about that. Let me just quickly show you a sample code for ODP 213, right? And I think everybody got this already. So yeah, initialize a running sum, go through less than string length buffer, just add up that ASCII character. I actually go ahead and reduce mod 31 as I do the add instead of just calculating the sum and reducing at the end. Is there any reason to do that? Is there any reason it's better or worse to keep reducing mod 31? Smaller numbers, meaning what? I think you got the right idea. Numbers could get very large, right? If I had 4 billion characters in my key that I was hashing, which is possible, right? This sum would overflow the size of an int. And then when I reduce mod 31, I might not get the right value. So it keeps this sum from ever being bigger than 30, and it takes away this potential limitation on how many characters I could have in my key. The downside, of course, is it takes more time, right? I'm doing this reduction every time that I add, and as we're learning in 215 this week, I could just as well add all of these up and then reduce mod 31 at the end. I'd get exactly the same thing as if I reduce each number, you know, each time that I add. Same result in the end, but this takes more work. But it makes it impervious to extremely large keys. And you know, you might be hashing something like a huge executable file that could be, you know, gigabytes in length. Okay, so back to our chat question. Right, the choice of hash function is important. So let's see what this hash does as far as storing things. So let's say we hash some key value pair, key 1, value 1. And let's say it's equal to, you know, a 2. So we try to store key 1, value 1 in here. And now let's hash key 2, value 2. And let's say that brings us right here. Okay, now we try to hash a third key, K3, and that brings us to this spot, which is in use. That was a loud noise. That brings us to this spot, which is in use. All right. So we need to rehash. And with our ODP213 hash function, right, we're going to try with a probe of 1. It's going to add 1 to our location. So the next spot we're going to try is the one right after where we tried originally. So this is going to be where we end up storing key 3, value 3. Now, let's hash key 4. And suppose key 4 also wants to go into the same location. Alright, we're going to get a collision with key 1. So we're going to, these are gibberish. We're going to rehash. Right? And when we rehash, it's going to give us the next location, and that's also in use. When we hash a next time, what's it going to do? It's going to give us the value of the original location, but it's going to add 4 to it. And so now we're going to try down here, and that's where it's going to store key 4. This is not a very good crypto hash, definitely. It's pretty reversible, which is something we don't want in most things crypto related. So yeah, that's a good observation. All right. So the upside of this is, we got a collision with trying our initial hash. When we rehash, we got a collision in trying the next spot. Instead of just trying the next spot, it jumps down further, right? Here it jumped down by 1. The next time it's going to jump down by 3. If we had gotten a collision there, it would have ended up jumping down by 5 before it tried again. I don't know how this would perform collision-wise in a crypto system. I'm not sure it would be horrible, but it's certainly pretty rudimentary. All right, so what's the effect of our probe value? When we start off with a probe of 0, that's, our first try. When we probe with a 1, we try a spot 1 space down from our original try. If we rehash with a probe of 2, now we try 4 spots down from our original, and then 9, and then 16, and then so on. And if we add another column here and we look at how much further we're jumping from our previous location, right? So our second probe attempt, we moved 1 spot from our previous. If we probe again, we're going to move down another 3 spots from there. If we probe again, we're going to move down another 5 spots. If we probe again, we're going to move down another 7 spots. So each time we probe, we're not only moving down the table, but we're moving down further than the last time that we probed. Right, and these sizes of jumps are increasing. They're increasing by 2 each time. We're doing calculus now, right? We've got x squared. We've got the derivative is 2x, right? Those are odd numbers, 2x plus 1. And then we've got the second derivative, which is 2. That's how big our first derivative is increasing. So calculus works, even with computer science. So what's the effect of this? The effect is, when we tried to hash key 4, we bumped into a little cluster here. Now, if we had simply tried, how about here, how about here, how about here, we might spend a long time trying to find an open spot because there's a big traffic jam here. By using this square, what we call quadratic probing, after a few tries in here, we start moving further away, and it tends to help us avoid building clusters. Linear probing, which would be basically just this, just add your probe number, that's going to be really bad for building clusters. Because if we bump into an already existing cluster here, we're just going to try consecutive locations and fill in the first one that's available. And now we've just added something else to the end of this big clogged up area. So quadratic probing works a little better. But we could, we could come up with all kinds of fancy hash functions that'll do better. So would this be ON for the insert? Depending on what n is, this will be order of the average size of your clusters, I believe, right? If everything is nicely distributed, and you've got something here and something here and something here, and your table is only 10% full, right? It's still asymptotically constant time, order 1. But if your table starts to get very full, this will increase. So if half your table was full, then it might be order 2, which is still order 1. It doesn't really get up to order n until this table is really, really kind of pathologically full. and any time that you hit, you're going to have to, go through a series of reattempts, and then, it would be order whatever the nominal size of your clusters are. But it stays pretty close to order 1 until it can't. So back to the overall picture. Yes, so if we do linear probing, we're guaranteed eventually we'll find an open spot if there is an open spot, right? If we just keep checking consecutive locations, eventually we'll find an open spot. And of course, when we get to the end, we roll back over to the beginning because we're reducing modulo table size -1, or modulo table size. So linear probing, we're guaranteed we'll always find an open spot. Quadratic probing, not necessarily. It depends on how you set up your table and what your table length is. And there's situations where you might, keep reprobing forever, but just keep using the same subset of spots and totally miss the fact that, there's an open spot up here. So we do need to be careful with choice of hash function, and that's a whole science in itself, figuring out what makes a good hash function. All right, so interesting question here. So when you resize the concept to something like 2n, is there a way not to have to reallocate and move the data? Like have the new memory be a linked list concept? Absolutely. So it depends on your goals. So yeah, what happens when your hash is totally full or full enough that it's kind of not doing a really great job and you want your hash to be bigger? If we just, add some extra stuff down here, unless we change our hash function, right, we're not going to use that extra stuff. But if we change our hash function, then when we try to find key 1, we're not necessarily going to come back here anymore. So you need to rebuild your hash. And you can do that by simply, going through and rehashing everything. And so that's an order n operation. You basically create a bigger table somewhere. You pull all of your things from here and you rehash them to store them into your new table. That's expensive, but it's a once in a while kind of operation. And typically what you would do is, if you're out of space in your table, make a bigger table that's, I don't know, 2 or 3 or 5 or 10 times larger. You can even study how quickly it's growing and pick a new size based on past performance. But that's expensive. Now, if you don't want to actually reallocate memory, there's things you could do. You could try to build a linked list out of this. You could combine probing with chaining so that at some point we could start having each of these entries point off to, another data structure. But in practice, you can actually do some of this in the background. As your table is starting to fill up, you can go ahead and you can create a new larger table and start copying values from here into that new table. But you don't have to stop using this table while that's going on. Now you need to mimic any changes you make to this in the new table that you're building, but that can happen in the background. And so if you start this early enough before, performance is completely bogged down here, you can silently in the background be building a larger table, and then once that's populated with all of your keys, now you just flip over and you start using that. And this is completely invisible to the user, right? This is this abstract data type firewall concept. This could all be happening behind the scenes, and all you know is that, your performance was starting to drop a little, and suddenly your performance is really good again. That was weird. I wonder what happened. Well, maybe it just reallocated a larger hash table space. Yeah, you're welcome. That didn't really address how to do that, but yeah, I think something like a linked list can be used in there. All right, other questions? So we're not going to worry too much about particulars of probing. And PA3, which I'm going to try to post later today or tonight, PA3 will be a hash table where we're going to use chaining instead of probing to deal with collisions. So your list will be a list of pointers to link. Your hash will be a hash of pointers to linked lists. So we won't be dealing with probing there, but let's develop these concepts further. All right, so searching. So here's your array of, whatever your structure is for hash table entries, which have a key and value pair and then some kind of in-use flag. Off topic, did you move temp G1 to a different location? Wait, never mind. Yeah, so I rebooted the server over the weekend and I forgot that wipes out the temp directory, hence the name. So I had to re-put G1 in there, and the version I put in didn't have symbols in it, or they weren't accessible, and so I put that in again. So yeah, it looks like a new copy, but it's the same G1. So G1 should be working. Speaking of G1, surprisingly few people have done the GDB quiz, which is due today, and I kind of thought, when I posted it, that people would do it then, so that you could ask questions and come to office and stuff like that. But it looks like the majority of people haven't actually started it, even at least as of this morning. So don't forget to do your GDB quiz. I think I set it to be due at midnight, but whatever Canvas says is the gold standard here. And hopefully that's pretty straightforward. Are the quizzes available after they are due so we can redo them for practice? I don't know how I set it up. I think they do not expire. They just have a due date. So if they go away, let me know and I'll open them up. All right. So so we went through adding yesterday, right? The executable for that quiz doesn't have debug symbols. It does have debug symbols. Check again. Run it again. So there was a period where it couldn't get to the debug symbols, and I tweaked it last night, and it should be working fine now. Yeah, let me know if it still doesn't. All right, so hash key 1 with a value of 0. There's key 1, there's value 1, that's in use. Hash key 2 with a value of 0, and we said that comes down here. There's key 2, value 2, that's in use. Hash key 3 with a value of 0, and that collides up here. And so hash key 3 with a value of 1, and that'll put it right here. And that's in use. All right, so what happens when we search? So search, let's say fetch or get. What do? We hash your key, we go to the table, we look to see if that spot's in use. If it's not, we're done. If it is in use, we check to see if the key matches. If it does, we're done. If it's in use but the key doesn't match, we have to do more work. So if we were trying to get the value associated with key 3, we would hash key 3. We'd come to this location in the table. We'd say it's in use, but the key is K1. we're not ready to give up yet. We rehash the key with another probe. That brings us to this location. It's in use. We check the key. It matches K3. We're done. We found it. So getting a key works like this. Set a probe value. That's going to be our attempt number. Hash our key with that probe. Check the table at that index. If that spot's not in use, we didn't find our key. If it is in use and the key in the table matches the key we're looking for, success. We found our key. Return the value and we're done. Otherwise, increment our probe number, go back up and try again. And a little note down here. Make sure you don't loop forever. So yeah, we need to know what's the maximum reasonable probe number. So if it's a good probe function that's guaranteed to check every location in your table, you could set that to, you know, the size of the hash table. And in general, we want to keep probing until, you know, we find a spot or we decide it's not in there. So if your probe function is guaranteed to try every spot, we simply need to know, you know, is there, well, that's restoring. Yeah, so I would just set it to the size of the array. Certainly if you set it to the size of the array, you're safe. You may end up checking the same locations multiple times if it's not a great function, but that's okay. Another option is, you know, when you hash with a probe of 0, save that index. And then as you're going through, check the new index that you're about to check, see if it's back to the original thing that you tried. And if it is, now you know you're cycling and you can give up at that point. That's probably a better way to do it. So set your first, save your first hash attempt somewhere, and then on subsequent hash attempts, see if you get back the same index as the first attempt. And if you do, you can stop right there and say, I didn't find it in the table. All right, so this is our get function. If we try to get key 3, right, we're going to hash with a probe of 0. That's what we did here. We come up here, and at that index, we find that it's in use, and the key does not match. So we increment the probe to a 1, and we rehash. That brings us to this entry. We check that it's in use, and the key matches. That's success. So we go ahead and we return the key value pair. Yeah, finding a good hash function is definitely 215. We'll actually talk about hash functions at the end of our current unit, which is on number theory. Well, we won't really talk about them much. We'll say the stuff we're saying here. All right, so suppose we search for something that's not in the table. So let's say key 4 hashes to right here. Check the table at the index. If not in use, fail. It's not in use, key 4 is not found. Let's search for a key K5. Let's say that hashes to here. Check that location. If it's not in use, fail. Well, that's not the case. If it's in use and the key matches, success. Well, it's in use, but the key is K2. It doesn't match, so that doesn't apply. So increment the probe number. So now hash with a probe of 1, and let's say that maps down to here. Same thing. It's in use, but the key doesn't match, so iterate again. And maybe when we hash with a probe attempt of 2, maybe that takes us down to here. And now we say, is it in use? Nope. Okay, not found in the table. Alright, is it making sense so far? So the only difference with probing is, you know, without it, you hash, check the table. If it's not in use, fail. If it doesn't match the key, fail, otherwise success. But here, you know, if it's in use but it doesn't match the key, instead of just saying it's not found, we go ahead and we rehash second attempt. And we keep doing that till either we find an empty spot or we find our key. Alright, so what about deletion? Let's see, question, you said we'll be doing a linked list version versus probe. Is one better over the other as far as performance? Why would we choose one over the other? Good questions that I don't necessarily have a general answer to. It largely depends on the requirements of the program and somewhat on the type of data. With chaining, you know, you're always going to be able to store something, right? You avoid the possibility of having to redo your hash function multiple times. But chaining, once you have one collision, right, once you collide with another key, you're down to order n guaranteed, where n is the number of things that hash to that location. So it's kind of a little bit like linear probing almost, but not as bad. The nice thing, one of the nice things about chaining, you know, where you're making a linked list, is you don't run out of memory. We don't have to grow the size of our hash table. We still might want to, right? If our linked lists end up being, you know, 1,000 nodes each, we might say, hey, this is out of control. We might want to grow the hash table. That's a little more complicated, and maintaining, you know, a linked list at each spot is a little more complicated. But the performance is pretty good. I think it depends on the nature of the data, though, as to, you know, can we find a hash function that will minimize, you know, multiple collisions. So I don't know. And yeah, we can put hashes inside each of these. You know, instead of chaining to a linked list, we could chain to another hash table. That would take us, you know, further down some bifurcation. I won't make you do that. I will make you do linked list of linked lists at some point, but not hashes of hashes. I'm not sure a hash of a hash is fundamentally different from a hash, though. Depends what you do, but I can envision ways you could do that. Alright, how do we delete? Let's say I want to delete key 2. So what should change in my hash table? Change the in-use field. If I clear that out, now when I try to search for key 2, I'm going to hash it, come down to this location, check the in-use. In-use is clear. It's not in the table. That works great. And if I delete something, I have to find it first. So, you know, to delete key 2, I hash key 2, find its index, make sure that's in use, and make sure the key is the one I want to delete. And if it is, clear the in-use flag. If not, rehash, check again. Keep doing that till either you find a node that's not in use, which means you're trying to delete something that's not there, or you find a node. So what happens if I delete key 1? I hash key 1 with a probe of 0. That takes me right here. I clear that in-use flag. Now I've just introduced a problem in my hash table. So what's the problem with my table as it is right now? I've deleted K1 and K2. I still have K3 in there. I cleared the collision. Right? If I say get K3, what's my algorithm going to do? It's going to hash K3 with a probe of 0. That's going to take me to this spot here. I'm going to check the in-use flag. In-use is cleared. My get algorithm is going to say, sorry, I don't see K3 in your table. Even though it is in the table, because I cleared that flag, my algorithm doesn't think that K3 is in there anymore. So the synopsis of this is, when we had something in this location, key 1, and we searched for K3, the presence of K1 caused us to not give up too soon. We tried to find K3 here. There was a collision. We tried again in a different location. We reprobed. When we deleted K1, we cleared this in-use flag. That stops us from continuing to search for K3 after one attempt. So we need to add something more to our hash table. We need a deleted flag. That's going to tell us, hey, there was something here, and it got deleted. So now our hash table looks like this. Here's a key. Here's a value. Here's an in use. And here's a deleted. All right, so let's put these back in. So we're going to initialize all of these in-use flags to 0, all of these deleted flags to 0. And now let's delete K1. So we're going to set in use to 0, but we're going to set deleted to 1. Now when we do our get, so let's say we want to get K3. So you're going to hash K3 with a probe of 0, which is going to point us here. Okay, instead of saying if it's not in use, we're going to fail, we're going to say if not in use and not deleted, then fail. So if this was a 0, that would mean nothing had ever been stored here, in which case we would not have gotten a collision trying to store K3. We can say K3 is not in the table. If it's in use and the key matches, success. Otherwise, increment your probe and try again. So we'll increment our probe and we'll rehash. And that'll take us here. And it is in use. We check the key matches. We found our data. So the deleted field tells us keep searching. Even though this node is not in use right now, something was here, you might have gotten a collision because it might have been in use when you tried to store the thing you're searching for. Does that make sense? Good so far, good, because that's pretty much it. So the last thing we need to do is worry about this deleted flag. And then we've kind of got the whole hash structure. So now when you delete a key, right, you search for your key. When you find it, set the in use to 0, set the deleted to 1. So our get algorithm looks like this, right? Keep checking locations in the table, but if it's not in use and it's been deleted, keep searching. If it's in use and the key matches, then see if it's the one that you're looking for. We'll only fail if it's not in use and it's not deleted. Or if, you know, somehow we've decided we've gone too many times, it's definitely not in here. So when we want to put something, we're going to do the same thing as we've been doing before, right? So, start off with a probe of 0, hash your key with that probe. Check the table at that location, right, that index. And I'm going to make an assumption in here. We're going to assume that this key is not in the table to begin with. Alright, so do a search first. So assume the key is not in the table to begin with. So if it's in use, increment your probe, go back. If it's not in use, or if it's marked as deleted, go ahead and save it right here. And if you manipulate your deleted flag correctly, you can simplify these conditions, but just to be really explicit, if it's not in use, right, well, we don't really need to worry about that. Let's just say if it's not in use, save it here. But what do we do when we save it here? Copy key and value. Set in use equal to 1. Let's clear the deleted flag. Set the deleted flag to 0. All right, makes sense? So the last, and so to initialize, right, you want to just go through, clear all your in use, clear all your deleted. That's pretty minor. This is a kind of uglifying detail, but you'll bump into it eventually, so let's just go ahead and get it out there in the open right now. So if we look at the in use and deleted fields, we can ask what's the meaning of these four combinations. If it's not in use and it's not deleted, this is a spot that's never been used. If in use is 0 but deleted is 1, this is a spot that had something in it, but that thing has been deleted now. If in use is 1, then the node is in use. And if in use is 1, we don't really care about the deleted flag, so you don't always have to clear it, but it's likely to be less confusing if you just, when a node goes back in use, clear the deleted flag. But we really only have 3 states, and we have 4 combinations, so that can look weird sometimes. All right, last thing to do with a hash is print out the contents, or somehow go through the contents of the hash. And this gets into a little more of a different topic, which we'll branch off on tomorrow. If all we wanted to do was print the contents of a hash, it's a pretty simple function, right? Make a print function that basically goes through each element, looks to see if the node is in use, and if it is, print out the key value pair. Okay, that's kind of a no-brainer. But we don't always want to print the contents of a hash. Sometimes we want to find the contents of a hash but do something with it, like throw it into a linked list, or build our own array out of it so that we can sort it by key or something like that. And if we just go through here and we print everywhere that we find a node that's in use, who knows what format we're getting, who knows what order these keys are coming out in, and so forth. So we'd like a way to be able to say, hey, I want access to all the key value pairs from this hash table. Right, we did this in 224 using a for loop. So we're going to get into the concept of an iterator, and we'll start with that tomorrow or Friday. I think tomorrow we'll talk about the next PA, and then we'll go back and we'll look at iterators. All right, good enough for now. Have a good one. I will see you next time. Thanks.